Hello Santvika, it's been so long since we both met.
Yes, how are you?
Good, what about you?
Yeah, I'm fine.
What are you doing in these holidays?
I'm totally confused.
About what you are so confused?
I completed my inter MPC. Now my parents are asking me to go with engineering. Even I am interested, but a small confusion.
Still, why you are so confused?
How the engineering life will be?
Hey, don't worry dear, the journey in BTech will be quite good. Take an example of our college, PVRIT Hyderabad, such a pleasant infrastructure with all the facilities. Even though it's a women campus, not at all less than any other. We have spacious classroom with a projector to make our understandings much better. Lab to work on the concepts what we have learned in the classrooms. Library facility with lot of books to gain knowledge. And number one in sports. Moreover, good supportive faculty and management. Have a look of our campus.
Wow, how great! But I'm worried about mathematics because I'm very poor and it's very difficult for me to pass intermediate level itself.
Oh, don't be so tensed. I'm also the same student with the same fear about college and mathematics and engineering. But to speak truth, mathematics what you are going to learn is much easier than what you have learned because in engineering the classes won't be like one side teaching and another side listening. It will be very interactive and most of the lecture will be taught you by showing live and real life examples. Me, after completing my first year BTech, I can say first year mathematics is much interesting, especially M1. M1 is all about matrices, eigenvalues and eigenvectors, sequence and series, calculus, multivariable calculus.
Oh, I never heard the topic name eigenvalues and eigenvectors. What is it actually?
Oh god, you're very much curious about your mathematics in BTech. No problem, maintain the same, you'll come to know everything.
Is learning mathematics in BTech only to write exam?
No, you're wrong. It is also helpful in our daily lives. Okay, then let me show you a few videos done by my friends which gives you an idea about M1 and you will get some confidence of entire mathematics and engineering. Matrices. What is matrix? And the answer is arrangement of the elements in m by n form is called matrix, where m is equal to number of rows and n is equal to number of columns. For example, this is 2 by 3 matrix because there are 2 rows and 3 columns. Order of a matrix. Number of rows by number of columns of a matrix is called order of matrix. If m rows and n columns, the matrix is m by n order. Types of matrix. Rectangular matrix, square matrix, row matrix, column matrix, null or zero matrix, scalar matrix, diagonal matrix, upper triangular matrix, lower triangular matrix. Rectangular matrix. In this matrix, number of rows is not equal to number of columns. M is not equal to n. Example: a matrix in which number of columns are 4 and rows are 3. Square matrix. In this matrix, number of rows is equal to number of columns. M is equal to n. For example, a matrix in which number of rows and number of columns are 4. Row matrix. A matrix containing only one row is called row matrix. Example: a matrix which contains only one row. Column matrix. A matrix having only one column is called column matrix. Example: a matrix which contains only single column. Null matrix or zero matrix. If every element of a matrix is 0, then it is called null matrix. Example: a matrix which contains every element as 0. Scalar matrix. A matrix in which all the elements in the principal diagonal are equal and rest of elements are 0 is called scalar matrix. For example, principal diagonal has the same value k and the rest are 0. Diagonal matrix. A square matrix in which, except the leading diagonal elements, all the other elements are 0 is called diagonal matrix. For example, in a matrix, every element is 0 except a diagonal. Upper triangular matrix. A matrix in which all the elements below the principal diagonal are zeros is called upper triangular matrix. For example, in a matrix where the elements above the diagonal have some values rather than 0. Lower triangular matrix. A square matrix in which all the elements above the principal diagonal are zeros is called lower triangular matrix. Example: in a matrix where the elements above the diagonal are zeros. Applications of matrix in daily life. Here is our first application. In a village, there is a successful fisherman named Ahmed. Many people respect and adore him because of his success in his business. Since there is huge success made to own a bootyard. His salary for the first 3 months of the year 2019 are 6,930 ringgits, 5,475 ringgits, 8,879.5 ringgits respectively. Table below shows the type of sea life that are sold for the first 3 months. So, to get started, we need to know how much Ahmad is getting paid per delivery. And here is the table which shows how much the Ahmad is going to get per each delivery. C stands for crab, P stands for prawns, F stands for fish. And here is the matrix which shows how much did he get. So these are the prices per delivery. Crab costs $3.2, prawn costs $3.5 and lastly fish costs $6 per delivery. Let us go with our next example. Ronaldo, Messi and Zlatan started practicing for their football match. Ronaldo passes the ball to the Zlatan. Zlatan to Messi. Messi back to Zlatan. Many more such passes are exchanged. Now, this is very easy to explain you diagrammatically. What if I want to explain a computer? Computer will not understand diagrams. So, we make a small table with 3 rows and 3 columns. We can have Ronaldo, Messi and Zlatan as rows, and to know for whom the ball has passed, Ronaldo, Messi and Zlatan as the columns. Let us assume players cannot pass ball to themselves. So these 3 elements will be zeros. So the one arrow passes from R towards M and R towards Z. Similarly, we fill the rest of the slots. What we see here is nothing but a matrix. Now this can be easily understood by a computer. By adding up all the elements, we get the number of passes. So this is how it is useful to make understand the computer easily.
Computer graphics is the computing field that involves the creating, storing and processing of image content via computer. It has a wide application in science, engineering, art and especially in the field of entertainment, movies and video games. In video gaming industry, matrices are the major mathematic tools to construct and manipulate a realistic animation of a polygonal figure. In hospitals, medical imaging, CAT scans and MRIs use matrices to operate. In programming, which is taught at the university, matrices and inverse matrices are used for coding and encrypting messages. A message is made as a sequence of numbers in a binary format for communication and it follows code theory for solving. It is also known as cryptology. Matrices are also used in robotics. In robotics and automation, matrices are the basic components for the robot movements. The inputs for controlling robots are obtained based on the calculations from matrices, and these are very accurate movements. In geology, matrices are used for making seismic surveys. They are used for plotting graphs, statistics, and also to do scientific studies and research in almost different fields. Now let us talk in deep about how matrices are used in computer graphics. The use of matrices in computer graphics is widespread. Many industries like cartoon architecture that were formerly done by hand drawing now are done routinely with the aid of computer graphics. Examples of matrix operations include translation, rotating and scaling. Other matrix transformation concepts like field of view, rendering, color transformation and projection. Translation. Suppose a 2D point is translated by an amount A in the x direction and B in the y direction, then the given matrix is multiplied with a 3 cross 3 matrix with elements 10A, 01B and 001. For For example, by multiplying the given matrix with the translation matrix, we can get the new coordinates. Now the given point changes from pxy to px dash y dash. Rotation. Suppose a 2D point is rotated about the origin anticlockwise by an angle theta, then the given matrix is multiplied by a 3 cross 3 matrix with the elements cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1 to give the new coordinates of the rotated figure. For example, multiplying the given matrix with the rotation matrix will give the new coordinates of the rotated figure. Now the figure will rotate from position O to O dash through an angle theta. Thus, matrices are very important to perform many operations such as translations, rotation, scaling, and these operations are used in computer graphics, which are ultimately used in video games. In conclusion, matrices play a vital role in computer applications, especially when it comes to graphics and image processing. Without the application of matrices, it would be very complicated to run various computer functions.
Welcome back to another episode, my dear friends. Today, we are going to talk about something really important and a simple concept, that is the eigenvectors. Last time I've asked you people, what does mathematics mean to you? And some have answered that it's the manipulation of numbers and manipulation of structures. And if I had asked what music means to you, would you have answered the manipulation of notes? Eigenvalues and eigenvectors is one of the topics that most of the students find unintuitive. Questions like why we are doing like this, what does this actually mean? It is not that eigenthings are particularly complicated and poorly explained. In fact, it's comparatively very straightforward, and I think most books did a very good job in explaining this. The issue isn't really made sense if you have solid visual understanding from many of the topics that preceded. Most important thing here is you know how to think about matrices, linear transformations, but you must also be comfortable with the things like determinants, linear systems, and change of basis.
Now, let's get started with our lecture and get a clear understanding on this eigenvalues and eigenvectors. In linear algebra, an eigenvector, also called a characteristic vector of a linear transformation. This is a non-zero vector that changes at most by a scalar factor when that linear transformation is applied to it. This corresponding eigenvalue is the factor by which the eigenvector is scaled. To define eigenvalue and eigenvectors formally, it is defined as if T is a linear transformation from a vector space V over a field F into itself and V is a non-zero vector in V, then V is an eigenvector of T. If T of V is a scalar multiple of V, this can be written as T of V is equals to X into V, where X is scalar in F, known as the eigenvalue or characteristic value or characteristic root associated with V. If V is finite dimensional, the above equation is equivalent to A into U, that is equals to X into U, where A is the matrix representation of T and U is the coordinate vector of V. The Mona Lisa example pictured here provides a simple illustration. Each point on the pointing can be represented as a vector pointing from the center of pointing to that point. The linear transformation in this example is called as shear mapping. Okay, do you understand the concept until now?
Yes, sir.
Alright, this is the complete overview of the chapter Eigenvalues and Eigenvectors. Now let's get started with the history of eigenvalues and eigenvectors. Eigenvalues are often introduced in the context of linear algebra or matrix theory. Historically, however, they arose in the study of quadratic forms and differential equations. In 18th century, Leonhard Euler studied the rotational motion of a rigid body and discovered the importance of principal axis. At start of 20th century, David Hilbert studied the eigenvalues of integral operators by viewing the operators as infinite matrices. The first numerical algorithm for computing eigenvalues and eigenvectors appeared in the year of 1929. Now let us know about the eigenvalues and eigenvectors of matrices. The topic is often introduced to students in the context of linear algebra courses focused on matrices. Furthermore, linear transformations over a finite dimensional vector space can be represented using matrices, which is especially common in numerical and computational applications. This is one such graph which explains the eigenvalues and eigenvectors of matrices. Now let us see some dynamic equations of eigenvalues and eigenvectors. In the first dynamic equation, we can see that the trace of A defined as the sum of its diagonal elements and is also the sum of eigenvalues. And in the second one, the determinant of A is the product of all eigenvalues. And these two are some simplest differential equations. And let's see some of the iterative methods to solve the eigenvalues and eigenvectors. One of them is this one. In this, if V is an eigenvector of A, then the corresponding eigenvalue can be computed as lambda equals to V star AV by V star V, where V star denotes the conjugate transpose of V. It is very much important to know the applications of any concept we learn to apply it perfectly. Eigenvalues and vectors have a wide range of applications. For example, in stability analysis, vibration analysis, atomic orbitals, facial recognition, and matrix diagonalization. Schrödinger equation is an application of eigenvalues and eigenvectors. An example of an eigenvalue equation where the transformation is represented in terms of differential operator is the time-independent Schrödinger equation in quantum mechanics. Molecular orbitals are also an application of eigenvalues and eigenvectors. In quantum mechanics, particularly in atomic and molecular physics, within the Hartree-Fock theory, the atomic and molecular orbitals can be defined by eigenvectors of Fock operator. Geology and glaciology are one of the major applications of eigenvalues and eigenvectors. In geology, especially in the study of glacial fill, eigenvectors and eigenvalues are used as method by which a mass of information of a class fabric's constituents orientation and dip can be summarized in 3D space by 6 numbers. Eigenvalues and eigenvectors are even applied in principal component analysis. It is also one of the major applications of eigenvalues and eigenvectors. This is all about the second chapter, Eigenvalues and Eigenvectors. Meet you in the next class with a new lesson.
Sequence and series. A sequence is simply a set of numbers in a particular order or a set of numbers which follows a pattern. The most basic example of a sequence is that of counting numbers 1, 2, 3, and so on. The numbers follows an increasing pattern. The 3 dots means the list goes on forever and they refer to as ellipses. The numbers don't necessarily have to be continuous to be a sequence. A list like 0, 5, 10, 15, and so on are also said to be in a sequence. What is the pattern here? Every number is increased by 5 to get the next number, a constant increment of 5. Let's take an example of a sequence which have an increment of 2, like 1, 3, 5, 7, 9, and so on. For your exams, there are just 2 things you need to know about any sequence. First, how do you find the nth term of a sequence? And second, how do you define the sequence? What do I mean when I say the nth term? Say I ask you the 31st term of the sequence. You have no time to write all the 31 terms to find that out. You need to have a formula, and yes, we have one. It is the first term plus n-1 times t. If t is the first term, n is term number. So if we want to find the 31st term, we just substitute that one in the place of n. And d is called the difference between any two continuous terms. It's called as common difference. It's extremely simple to derive this formula, but you don't really need it for your exam. So don't dwell too much over it. In this example, as the first term is 1 and the common difference is 2, the nth term will be n plus n-1 times 2. How do you define a particular sequence? Expanding this gives us 2n minus 2 and we add the 1. This gives us 2n minus 1. Here, n takes the value of all natural numbers. Don't forget, n is the term number. If we call this sequence as the first term of the sequence, will be written as s1. To find the first term, all we do is substitute 1 in the place of n. We get 2 times 1 minus 1, and 2 minus gives us 1. Now, with this formula, try finding the 9th and 21st term of the sequence. The 9th term will be 2 times 9 minus 1, which equals to 17, and the 21st term will be 2 times 21 minus 1, which equals to 41. 41 is the 21st term of the sequence. So, to define the sequence, we just use the nth term formula and substitute the values of first term and the common difference. We will look at a couple of sequence examples in the next part of the section. What do we mean by series? In simple words, it is the sum of terms in a sequence, not sum of random terms. There have to be terms in a sequence. Let's say we have series like 1 plus 2 plus 3 plus 4 and so on up to n. This is a series as 1, 2, 3, 4 and so on form an arithmetic sequence. This series is defined as n times n plus 1 over 2. We have seen this formula before, n over 2 times first term plus the last term. There are 2 more common series which we should know about. And the first is 1 square plus 2 square plus 3 square and so on up to n square. This is the series as it is the sum of terms in a sequence. The sequence is n square. Each number is the square of the term number. The sum is equal to n times n plus 1 times 2n plus 1 the whole divided by 6. So, if we want to find sum up to 6 square, we just substitute 6 in the place of n to get the sum. And the last kind of series we need to know about is this one, sum of cubes of natural numbers. To find this series, we simply have to square this one. N times n plus 1 over 2 the whole square. So, if you want to find sum of first 4 terms, we put 4 in the place of n and get 100 as the answer. Remember these 3 formulas for your exams, you will end up saving a lot of time. Let's try out an example. How do we find the sum here? Pause the video and give it a try. We have seen a formula for the sum of terms of this kind of a sequence. It's n times n plus 1 times 2n plus 1 over 6. What is n here? Yes, it's 10. Based on the formula, this is what we get. N times n plus 1 times 2n plus 1 over 6. This can be simplified to 10 times 11 times 21 over 6. Solving it, we get the sum as 385. Knowing a formula simply helps us to get the answer quickly.
This is Ahmad and his family.
They love to travel around the world. Ever since 2012, where Ahmad's age was 20 years old, he started to travel by himself to a different country every 3 years. Ahmad decided to stop traveling in 2056 when his age is 65 years old.
For every country that Ahmad went, he wants to write journals of his journey. So, he wants to know how many journals will he produce from the year he started traveling, which was in 2012 until 2056.
I think I know the solution.
Based on the calculations, Ahmad will produce 15 journals throughout his 45 years of traveling alone to different countries every 3 years.
Welcome to the world of calculus. Let's get started with our lecture.
Students, as we have completed third unit, tomorrow everyone come prepared with fourth unit calculus so that we can complete it fastly and remember that I will ask you questions.
Okay, sir.
Students, now let's get started with our fourth unit calculus. Before getting into the concept, first we need to know why calculus. So, for an example, if a girl drops a ball from her hand and questions herself what will be its speed as it reaches its midway of the path. For example, height is 1 meter, 50 centimeters to reach the midpoint. She knows that it took 1 second to reach the midpoint. With this information, does she find the speed of the ball at the end point? You also say that speed is equals to distance traveled by time taken. But this is wrong. This might be correct if the speed of the ball is constant, but she actually got the average speed of the ball. Can you try finding instantaneous speed at point B, that is the end point? So let us see what happens to the ball at instance B. At the instant, the ball is at B. So the distance traveled is equals to 0 and time taken to the cover distance is also equals to 0. As we know, instant speed is equals to distance traveled by time. By the values which I have mentioned above, distance traveled is 0 and time taken is also 0, which gives the answer undefined. This doesn't make any sense. So here arises a question that how to find speed of the ball. The only thing I'll say is keep calm and learn calculus. Calculus is branch of mathematics that help us answer this question. How? We'll see this in later session of our course. But wait, another thought puzzled that girl. She wonders why the ball reached the floor. She knows mathematically that the ball should never touch the ground. So what was her thought process? Let's see. Suppose she drops from height 1 meter. To come onto the floor, the ball has to reach the point B first. That is, there are an infinite number of steps that the ball have to perform, so it takes infinite time. She thinks the ball takes infinite time. If this is the case, the ball should never reach the ground. This is not the thought which only puzzled her. Centuries ago, the same thought puzzled Greek philosopher Zeno of Elea. This is usually referred to Zeno's dichotomy paradox. We know ball touches the floor, but the mathematical calculations tell us that the ball should never reach the floor. Again, satisfactory explanation is provided by calculus. So, my dear students, calculus helps us with analyzing things in motion. For example, calculus helps us to find instantaneous speed of object, angle at which to throw an object to cover maximum distance, and area of shapes, and etc. Students, in our next session we will get to know some of calculus.
If you are watching this, then you must finally be learning calculus. First of all, an excellent work by you. It is not that easy to learn all the required algebra and trigonometry to make this happen. So, before we get down to the business, let me give you an overview of what to expect from this. Alright, so what is calculus? When it comes to the topic calculus, you find it pretty much different from the rest of the maths topics probably you have studied so far. To get a better understanding on this topic called calculus, let us look at a simple example. What is calculus? Calculus is the mathematics that deals with the change. Let's take a look at simple example to find out. Let's suppose that we have a car traveling 25 kilometers per hour. If it drives for 3 hours, then we can find that total distance is 75 kilometers. But this is not the change we are looking for. Now let's suppose that due to the road conditions or the driver, the car is speeding up and slowing down. In other words, its speed is changing. In other way, we have a more realistic problem that how can we determine how far the car will travel in 3 hours? This answer lies in calculus. This is just one example where we want to be able to mathematically handle the change. To tackle the problem of changing, calculus picks up three major tools. These tools are limits, derivatives, and integrals. There are many more things to learn in calculus. Well, these are the most essential things to learn. Limits are the tools we use to describe precisely how a function approaches a value. Derivatives are the tools we use to describe how our value changes. Integrals are the tools that gives us the area underneath the curve of a function. Well, using these three tools, calculus can solve any variety of different problems like optimal viewing and preparing a perfect soup can. All the three tools of calculus are internally related to each other. In general, they seem to be much different, but derivatives are built from limits. Integrals can be viewed as inverse of derivatives. Of course, to learn all these, we have to start digging deeper into the subject. Do you know? Calculus is the better way to determine the world around us, especially when it comes to change. After learning why should we use calculus and what is it, let us now know about the types of calculus. Calculus has two major branches. One is differential calculus and other is integral calculus. Differential calculus concerns about instantaneous rates of change and growth of curves, while integral calculus concerns accumulation of quantities and areas under or between curves. These two branches are related to each other by fundamental theory of calculus. They make use of fundamental notions of convergence of infinite sequences and infinite series to a well-defined limit. Now moving on to the principles of calculus. Firstly, when we talk about the principles of calculus, we used limits and infinitesimals. Calculus is usually developed by working with a very small quantities. Historically, first method of doing so was infinitesimals. These are objects which can be treated like real numbers, but which are in some sense infinitely very small. In late 19th century, infinitesimals were replaced within by epsilon delta approach to the limit. When we talk about limits, limits describe the value of a function at a certain input in terms of its values at nearby inputs. Now, let's learn more about the types of calculus. Firstly, talking about differential calculus, it is the study of definition, properties, and applications of the derivative of a function. The process of finding derivative is differentiation. The most common symbol is apostrophe, like mark called prime. This is a small graph that represents the differential calculus. Now coming to integral calculus, it is the study of definition, properties and application of two related concepts, the definite integral and the indefinite integral. As we know, the symbol of integration is elongated s, and this is how we denote the definite integral. We read it as integral a to b f of x dx. Here a and b are the limits of given integral. And this is how we denote an indefinite integral. Indefinite integral doesn't have any limits, and we read this as integral f of x dx simply. See, it is of no use learning the concepts, formulas without knowing where to apply them and how to apply. So, let us now know some of the applications of calculus here. Basically, we know that calculus can determine the whole world, so almost everywhere calculus is used in some or the other way. Let us see some of those examples now. Basically, in every branch of physical science, actuarial science, computer science, statistics, engineering, economics, business, medicine, demography, and in other fields wherever a problem can be mathematically modeled and an optimal solution is desired, the calculus is applied in all those areas. Physics makes a particular use of calculus in the concepts like classical mechanics and electromagnetism, etc. Calculus can be used in conjunction with other mathematical disciplines. For example, it can be used with linear algebra for best fit. It can also be used in probability theory, analytic geometry, and etc. As a part of the major applications of calculus, the logarithmic spiral of a nautilus shell is classical image used to depict the growth and change related to the calculus. For now, calculus might be difficult with new terms and procedures. But calculus is the better way to determine the world around us, especially when it comes to change.
topic that you're about to study? Well, I could say it's all about multivariable functions. That doesn't really answer anything because what's a multivariable function? And basically, the kinds of functions that we're used to dealing with in the old world, in the ordinary calculus world, will have a single input, some kind of number as their input, and then it outputs just a single number. And you would call this a single variable function, basically because that guy there is the single variable. So then a multivariable function is something that handles multiple variables. So, it's common to write it as like x, y. It doesn't really matter what letters to use. And it could be, x, y, z, x1, x2, x3, a whole bunch of things. But just to get started, we often think just two variables. And this will output something that depends on both of those. Commonly it'll output just a number. So you might imagine a number that depends on x and y in some way, like x squared plus y. But it could also output a vector, right? So you could also imagine something that's got multivariable input, f of x, y, and it outputs something that also has multiple variables. Like, I'm just making stuff up here, 3x and, 2y. And this isn't set in stone, but the convention is to usually think if there's multiple numbers that go into the output, think of it as a vector. If there's multiple numbers that go into the input, just kind of write them more sideways like this and think of them as a point in space. Because, when you look at something like this, and you've got an x and you've got a y, you could think about those as two separate numbers. Here's your number line with the point x on it somewhere. Maybe that's 5, maybe that's 3, it doesn't really matter. And then you've got another number line, and it's y. And you could think of them as separate entities. But it would probably be more accurate to call it multidimensional calculus, because really, instead of thinking of, x and y as separate entities, whenever you see two things like that, you're going to be thinking about the xy plane and thinking about just a single point. And you'd think of this as a function that takes a point to a number, or a point to a vector. And a lot of people, when they start teaching multivariable calculus, they just jump into the calculus. And there's lots of fun things, partial derivatives, gradients, good stuff that you'll learn. But I think first of all, I want to spend a couple videos just talking about the different ways we visualize the different types of multivariable functions. So as a sneak peek, I'm just going to go through a couple of them really quickly right now, just so you kind of whet your appetite and see what I'm getting at. But the next few videos are going to go through them in much, much more detail. So first of all, graphs. When you have multivariable functions, graphs become three-dimensional. But these only really apply to functions that have some kind of two-dimensional input, which you might think about as living on this xy plane, and a single number as their output. And the height of the graph is going to correspond with that output. Like I said, you'll be able to learn much more about that in the dedicated video on it. But these functions also can be visualized just in 2 dimensions, flattening things out, where we visualize the entire input space and associate a color with each point. So this is the kind of thing where you'd have some function that's got a 2-dimensional input. It would be f of x, y. And what we're looking at is the xy plane, all of the input space. And this outputs just some number. Maybe it's like x squared. This particular one is an x squared, but that and maybe some complicated thing. And the color tells you roughly the size of that output. And the lines here, called contour lines, tell you which inputs all share a constant output value. And again, I'll go into much more detail there. These are really nice, much more convenient than 3-dimensional graphs to just sketch out. Moving right along. I'm also going to talk about surfaces in 3-dimensional space. They look like graphs, but they actually deal with a much different animal that you could think of it as mapping 2 dimensions. And I like to sort of spush it about. And we've got kind of a 2-dimensional input that somehow moves into 3 dimensions. And you're just looking at what the output of that looks like, not really caring about how it gets there. These are called parametric surfaces. Another fun one is a vector field, where every input point is associated with some kind of vector, which is the output of the function there. So this would be a function with a 2-dimensional input and then 2-dimensional output, because each of these are 2-dimensional vectors. And the fun part with these guys is that you can just kind of imagine a fluid flowing. So here's a bunch of droplets like water, and they kind of flow along that. And that actually turns out to give insight about the underlying function. It's one of those beautiful aspects of multivariable calc. And we'll get lots of exposure to that. Again, I'm just sort of zipping through to whet your appetite. Don't worry if this doesn't make sense immediately. And one of my all-time favorite ways to think about multivariable functions is to just take the input space. In this case, this is going to be a function that inputs points in 2-dimensional space, and watch them move to their output. So this is going to be a function that also outputs in 2 dimensions, and I'm just going to watch every single point move over to where it's supposed to go. These can be kind of complicated to look at or to think about at first, but as you gain a little bit of thought and exposure to them, they're actually very nice, and it provides a beautiful connection with linear algebra. A lot of you out there, if you're studying multivariable calculus, you either are about to study linear algebra, or you just have, or maybe you're doing it concurrently. But understanding functions as transformations is going to be a great way to connect those two. So with that, I'll stop jabbering through these topics really quickly, and in the next few videos, I'll actually go through them in detail, and hopefully you can get a good feel for what multivariable functions can actually feel like.
Very nice. After talking to you, seeing your videos and about your college, I feel much better now. Now I think I can utilize my holidays.
Yes.